Okay, so we are starting a brand new topic and we have a brand new writer. Let's shift my position a little bit, that's better. Okay, so we are going to start talking about convolutional codes. Okay, and towards the end of last lecture I gave you a simple high level reason for why this is interesting. It turns out soft ML decoding can be done efficiently. Okay, and of course soft bitwise MAP is also efficient. So, both of these are efficient for convolutional codes. Okay, so that is the main selling point for these codes, and you will see on top of this they also have an amazing advantage that they are really simple. Okay, so they are the simplest possible codes, and not simplest possible codes of course, but they are very simple to describe and simple to describe the decoding, very intuitive and very nice, and you can clearly understand what happens with these things quite easily. Okay. So, we are going to begin with an example. Okay. So, I will give you an example of a convolutional code, and it will be a very typical example. Any other convolutional code will be a minor modification of that. We will also define it generally later on, but an example is the best place to start. Okay. So, let us begin with an example. Okay. And I will start by drawing an encoder. Okay. So, instead of just defining the code, so if you remember till now we were defining the code directly, code is the list of all code words. Now, I will define the encoder for this code. Okay. Of course, that also defines the code in a way, right. So, it is not a bad definition. So, the encoder that I am going to draw will involve D flip flops. Okay, all of you must be familiar with what a D flip flop is. Basically, it is a delay element. Okay, it will have a memory of 1 bit and it will hold it for 1 clock cycle. Okay, so it will be like a clocked sequential digital circuit. Okay, so let me draw that. Okay, so I have 2 D flip flops. Okay, and they are connected up like this. There are 2 outputs. Okay, and the second one looks like this. Okay. So, it's kind of an ugly looking diagram of the encoder. I am sure you will find better pictures of the encoder. So, this is the input and this is output 1 and output 2. Okay. So, this is the encoder. So, what happens is bits are clocked in from the input side. Okay, at every clock you send one input bit in and they are clocked out on the output side. Okay, so that's the high level picture here. So, I think you've seen enough digital systems to know that that's what's happening here, but anyway let me emphasize that once again. Bits are clocked in and clocked out. At the input side, at the output side, bits are clocked out. Okay. Of course, the clock is not shown. Okay, it's supposed to be there. Okay, I am not showing it explicitly anywhere. It's supposed to be there. Okay, there is a clock which is running, and every tick of the clock or every state of the clock, it's going to keep shifting a bit inside, and an output bit is 2 output bits are going to come out. Okay, so we need some notation. I'll call the nth input bit as some un. Okay, so at the nth clock, the input is un. Okay, so these are all bits. So what will be the what do I have to write here? What will happen here? un minus 1, right. So, it would have been the input in the previous clock, it would have, after a delay it will be there. What about this guy here, un minus 2. Okay. So, once you figure this out, it is a simple D flip flop, you know exactly what is going to happen. The outputs are also easy to write down. Okay. So, we have two outputs. So, we will have a notation like this for the nth output Vn1, this will be un XOR un minus 2. Okay. By the way, this is XOR. Okay. So, I think it is standard. So, I have not written it down. Okay. So, the second output is what? Vn2 is going to be un XOR un minus 1 XOR un minus 2. Okay. So, that is the second output bit, right. So, I am sure you agree with me on this word simple. Okay. So, it is a very simple code. I mean, if you look at the LDPC code for instance, its encoder is definitely not going to look anything remotely close to this, right. It is going to be quite big and you have to remember a lot of things, you will do a lot of things for that, but for the convolutional code the encoder is so simple. Okay. And this is a main reason, this is a huge advantage in practice several times. Okay. So, you might want some system where the transmitter is maybe very weak, so to speak. Okay. It is relying on, let us say, some very poor energy source, it cannot sustain for a long time. So, you want to have an encoder which is really simple, okay, and this will satisfy that constraint. Okay. So, if you look at the number of gates in this implementation, how many gates are in a D flip flop? Okay, some number which is you can count in one hand, right. So, it is a small number. Okay. So, you have 2 D flip flops and 2 XORs, right. So, about 10-15 gates you will be able to easily do this entire implementation and there will be a clock and it is a dirt cheap circuit. Okay. It will work on and on forever. Okay. So, that is a big advantage with convolutional codes. Okay. So, the big point is, are they any good? How well do they do in a bit error rate or block error rate situation? Okay. So, we will see when you implement soft ML decoding and in fact you implement bitwise MAP or any other decoder, it will work really well. Okay. So, we will see that also. Okay. So, this is the picture, hopefully this picture is clear. So, now you can see some generalizations of this picture. Okay. So, in general, how will a convolutional encoder typically look? Okay. You will have more than 2 D flip flops, you can possibly have some mu D flip flops, okay, and then how many outputs can you have? As many as you want, maybe 3 or 4 or 5, okay, and then let us say one input always, okay, and then it is just a question of connecting up the different points of the D flip flop outputs to these XOR gates and getting your output. Okay. So, that is the generalization. Okay. If I have to present it in the most general form, there will be a lot more notation, but definitely not much insight is lost with this example. Okay. So, you get the idea of what is happening here. Okay. Okay. So, the next important thing to remember is this seems like an encoder which is going to take a stream of input and keep on putting out 2 streams of output. Okay. But in practice with codes it is not going to work this way. Okay. There is going to be a block of message bits, some k bits, okay, and they have to be converted into so many bits before transmission. That is one important constraint in practice, right. So, you cannot keep on and on encoding all the time, right. So, there are other things that have to happen, communication has to be started and stopped and so many other things will go wrong if you have it like a stream. So, you have to stop and start. So, we have to convert this picture into a block coding picture, okay, that is one thing, and the other thing is there are 2 streams of output, okay, and they have to be interleaved also and sent out. Okay. All these things have to be taken care of in an actual operation. So, let me write down how that works first and then we will see other descriptions of what happens here. Okay. So, the input you can think of as, so first thing I should start out with is the state of the encoder. Okay. So, what is the state of the encoder? Okay. So, it is the state of any digital system. What is the state of digital system? To look at all the outputs of the D flip flops, put them together, how many ever bits you have, that is called the state. Okay. State of the encoder is basically 2 bits. Okay. So, you can call it S1, S2 if you like. Okay. So, basically it is 2 bits in this example, of course In general, it will be as many bits as the number of D flip flops that you have. Okay. So first question in an actual implementation is, what is the initial state? Okay. So it is typical to take the initial state as zeros. Okay. So you are going to put initially zeros in your D flip flop output. So we will assume that the initial state is 0 in implementation, and then you have so many number of bits coming in. Okay. So let us say k bits of input are going to be clocked in. Okay. So it is very common and very important to terminate your state, terminate your encoder finally in the all 0 state once again. Okay. Right. If you keep clocking in k bits, at the end of k bits, state is not guaranteed to be in the all 0 state. Okay. So it is usual in convolutional codes to manually put in 2 further bit inputs to force the state back to all 0 state, so that you start at the all 0 state and end at the all 0 state. Okay. So that is good for a lot of description, and in practice that is always done. Okay. So that is called termination. So we will do that in practice as well. Okay. We will do that when I describe it. Okay. So if you have k bits of input, okay, so it is a bit tricky how I write it. Okay. So I am going to write it as u1 u2 all the way to uk. Okay. But what does this mean? Which bit will go in first? u1 will go in first. Okay. So maybe it is good to write it as u0. Okay. So let me write it as u0. Sorry about that. I will start with u0 and then go all the way to uk minus 1. Okay. So that is better. Okay. u0 u1 all the way to uk minus 1. Okay. So this is my k bits of input. Okay. My initial state is going to be 0 0. Okay. So the final state will be what after k bits? State after k bits will be what? Yeah, after k bits of input will be uk minus 2, no, uk minus 1, uk minus 2, right? Right. And I do not want this. Okay. So this is not, you cannot end in a random state. It turns out it is bad for the decoder. Okay. So you want to go back to the all 0 state. So you have to add along with the k bits of input 2 additional terminating bits, which in this case the way I have drawn it will always be 0 0, so that you can take it back to the initial state. Okay. So the actual input will be, okay, actual input for all 0 state termination will actually be u0 u1 all the way to uk minus 1, and then I will add 2 zeros. Okay. In the general case, when you have, let us say, mu d flip flops, how many zeros will you have to add? Mu zeros, that is all, it is no problem. Okay. So you only do that, that is what will happen. Okay. So now let us look at the output. This is being clocked in. So the output 1, okay, so maybe we can call this as some vector u, and this will be u0 0. Okay. So we can do that. The output 1 will be, so we not write n, the vector v1, it will be v1 0, v2 0, oh sorry, did I get that right? No, v1 1, so on till v1 k minus 1. Can I stop here? No, right. So when I put in the zeros also I will get some output, and I have to retain that also. If I want a complete picture, I have to retain that also. So in fact you will have a v1 k and a v1 k plus 1. Okay. And the output 2 will be v2, and that will again once again be v2 0, v2 1, v2 k minus 1, v2 k, and v2 k plus 1. Okay. So the actual code word output that is actually going to be transmitted will be an interleaved form of these two things. It will be basically V10, V20, V11, V21. I will write one more. Okay, so let me not write one more. That's good enough. Okay, all the way to V1 k minus 1, V2 k minus 1, V1 k, V2 k, and then V1 k plus 1, V2 k plus 1. Okay, that is my actual output. Okay. So, these two are the outputs corresponding to the first time instant, 0th time instant. These two are the outputs corresponding to the second time instant, okay, time 0, so to speak. Okay. So, if your index time, this will come out at time 0, time 1 and so on, okay, and the last one will be time k plus 1. Okay. So, your message was actually k bits long, that is the message that you have. You can't say the 0 0 is the message. Okay. So, it is not any random message, it is known at the receiver. So, it is only k bits long. How many bits of code word do you have? 2k plus 2. Okay. So, the actual rate of this code in the 0 termination operation, okay, 0 terminated rate is actually k by 2k plus 4, right. So, you have these 4 additional bits that have to be sent for k bits. Okay. So, this is the 0 terminated rate, while the design rate is what? Design rate is half. Okay. So, if you look at the encoder rate is half, right. For at every time instant it seems to be doing half, but when you actually operate it, you will get this penalty. Okay. So, there will be this penalty because of the 0 termination, that is okay. Okay. So, why is 4 not a big deal? Yeah, it's like it's obvious to many people. If k becomes 1000, then clearly the 4 is not going to hurt you at all. But remember, keep in mind, I mean, you may not know this, but convolutional codes are even used with very low block lengths. Okay, k could be 8 or 10 or something, and with that case, things like 4 will matter a lot. Okay. So, in general, okay, so this is the picture for the specific rate half code. In general, if you have, let us say, so in general, if you want to generalize it, okay, so it's quite easy to do that. You might have an encoder might have mu flip flops, if it does so, then it's called since mu is called memory. Okay. So, for obvious reasons it is called memory of the encoder. Okay. So, the encoder might have mu flip flops, and input we will keep as 1. Okay. For the purposes of this course, we will keep as 1. Of course, there is other theory for more than one input also. It is possible to have 2 or 3 inputs, and then you need a slightly more complicated picture, but for this course we will keep input as 1. Okay, just one stream. In output in general can be some m streams, right. Okay. So, if this is true, the design rate is 1 over m. Okay. So, that is the design rate. What will be the 0 terminated rate? Okay. So, these are very easy things to figure out, but anyway, let us do that once and then we will do that. It is going to be k for k bits of input. Okay. So, 0 terminated rate actually depends on the length of the message. Okay. For k bit input, k by mk plus m times mu. Is that okay? Okay. So, if you put numbers like, for instance, m equals 2, mu equals 6, mu equals 6 is a popular number. Okay. in practice in many standards mu equals 6 is a popular number, m equals 2 also is a popular number. Okay. If you put k equals 8, what happens to the design rate? Well, might be 1/2, but the actual rate is going to be 8 by 16 plus 14, no 12, my multiplication tables are getting rusty. Okay. So, even though you are saying the rate is 1/2, because of this extra 12 bits, what does the rate actually become? It's become, yeah, it's become less than a third. Okay, it's become less than a third. So, this is less than 1 by 3. Oh my god, less than 1 over 3. Okay. So this is a problem. In practice people deal with it differently, but anyway, so we will just assume 0 termination all the time. So, things like 8 are dangerous, 8 bits of input are dangerous when you want to do 0 termination. You may not have real control over your rate then. Okay, so hopefully the operation is clear. So, let us go back and look at the encoder circuit once again. So, in general for a convolutional encoder, if you have rate 1 over m and memory mu, there are going to be d flip flops, one input stream, and if you have m outputs, m different XOR gates at which some connections are made. Okay, so that is the idea. Okay. So, the question is, why is this called convolutional?
Convolving with some stream of ones and zeros.
All of you must have seen, maybe hopefully, enough linear system theory, right. So, this is basically some kind of a very linear system. Okay, and you can think of an impulse response, it is a discrete time linear system, except that you might be used to systems where the impulse response is real numbers, right. So, you are used to real numbers. Here the difference is it is all bits, everything is modulo 2. Other than that, everything else is the same, it is same standard linear function theory will apply. Okay. So, if you send an impulse as input, what is an impulse as input? 1 followed by a bunch of zeros, you will get a certain response at output 1 and output 2, that will be impulse response 1 and impulse response 2. Okay. If you now do an arbitrary input, how can I compute the output? Simply take that input and convolve with the impulse response, you will get the output. Okay. So, it is all linear, same thing will hold. Same thing you can do at output 2 also. You have an impulse response corresponding to output 2 and then you do that. Okay. So, what are these impulse responses? Let us try to find them. Maybe I call it G1. What is G1? Okay. So, it is just going to be 1 0 1. Okay. So, that is it, right. What about G2? 1 1 1. So, these two things are the impulse responses. Okay. So, in general, if I want to find the input for un, I have to take un and then convolve with gn1. So, this sequence u, so if you think of the sequence itself as u, okay, the sequence v1 is simply going to be the sequence u convolved with g1. Okay. So, the sequence v2 is going to be u convolved with g2. Okay. So, these are standard ideas, not too difficult. Okay. So, the convolution is also very easy to do. Basically, this convolution will mean un plus un minus 2. This convolution will mean un plus un minus 1 plus un minus 2. Okay. Exactly the same thing, we are just saying it in multiple different ways. Okay. So, the nice thing about convolution is you can also think of it as polynomial multiplication. Okay. So, you go to this transform domain, usually you do the Z inverse. Okay. So, Z inverse is common when you do real numbers. Okay. When you have binary and all that, instead of Z inverse people usually use D, capital D. Okay. So, you can go to the D notation, okay, which is the D transform, so to speak, of this impulse response and get capital G1 of D and capital G2 of D, and then you do a D transform on U to get a U of D. How will I find V1 of D? Simply do U of D times V of D. Okay. So, that is the idea. Okay. So, let us do that a little bit more with one more example. So, let us do this. This is we are trying to do D transform notation, so to speak. I mean, I have to just say it is notation, it is nothing more than that at this point. Okay. So, we get two impulse responses, Okay. So, you think of the sequence un as u of d. What is u of d now? U of d is basically summation ui d power I. Okay. So, I will go from 0 to wherever. Okay. So, 0 to let us say capital, I do not know, I will just put capital K here, okay, just to keep something definite. Okay. So, I have 2 D flip flops, one output is these two things, the other output is all 3, right. Okay. So, I can write V1 of D, the D transform of the output here, as U of D times capital G1 of D. What will be this guy? G1 of D will simply be 1 plus D squared. Okay. So, remember G1 was simply 101. So, the D transform will be 1 plus D squared. Okay. So, it is all the same thing. I mean, I am just saying the exact same thing. The basic thing I am saying is V1 n is un plus un minus 2. You can write it in so many different ways. Another way of doing it is to write it as u of d times G1 of d, where G1 of d is 1 plus D squared. Okay. So, it is a D transform notation. Okay. When you learn it in DSP, I am sure they told you that this is the greatest revolution ever in signal processing, but it is all very simple stuff. I mean, it is not very complicated. Okay. So, u of d times G2 of d, and this G2 of d will now be 1 plus D squared, which corresponds to the impulse response 1 1 1. Okay. It is really no big deal here, and you get the same equation back. I mean, if you just plug it in, you get the exact same case back. Is there a question?
Summation. The rest of
I have
them
just
will
put
be
a capital K there. It's okay. It's not the small k. It's not related to the previous k. Okay. So, this is some, maybe if you want, I will use some other notation there. I just wanted something just to define what the D transform is. Okay. So, how many ever you have there, you have to do it. Of course, if you 0 terminate, you have to put the zeros also, but the zeros do not show up in the D transform anyway. So, it does not matter. Okay. All right. So, this is the transform notation. So, there is again once again a shorthand notation for this. So, what you do is you can do a D transform generator matrix. Okay. So, this is pretty important, because you get some nice tricks that you can play once you do this. You have a generator matrix in D transform that is basically G1 of D, G2 of D. Okay. What does this generator matrix do for me? If I want to find V1 of D and V2 of D, what can I do? I can simply take U of D and multiply it with the generator matrix G1 of D, G2 of D. Okay. So, this is for this simple and nice reason, it is called the generator matrix. So, let us maybe do one quick and dirty example. Okay. So, let us say U, the input code word. So, I am going to use all these notations interchangeably. Okay. So, if I put a U with the bar underlined, it means I am thinking of it as a vector. If I say U of D, I am thinking of it as the polynomial in D transform notation, okay, extra. Okay. So, let us say U is 1 0 1 1. Okay. Okay. Go ahead and tell me what U of D will be. What is U of D? 1 plus D squared plus D power 3, right. So, what is V1 of D going to be? It is basically U of D times 1 plus D squared, right. So, I have to multiply U of D with 1 plus D squared. Okay. So, it is quite simple. If I do that, I am going to get 1 plus D squared plus D power 3 plus D squared plus D power 4 plus D power 5, and that will be 1 plus D power 3 plus D power 4 plus D power 5. It is not too difficult to figure out, and V2 of d you can find very similarly, it is going to be u of d times 1 plus d squared. Okay, so it is basically this guy plus d times that. So, it is going to be 1 plus d power 5. Okay, so if you do the multiplication, you will get that. Okay. So from here, if you want, you can figure out the code word output. What will be the code word output? 1101 00 10 10 11. What will happen after this? How many should I put out? That is it, that will be the end. Okay. Seems a little surprising, but you see now why the zero termination is nice. You have to do the zero termination because this polynomial formula will work very nicely. Okay. If you did not do it, it will be a little bit more complicated. Okay, so we have made the polynomial formula kind of work with a zero termination. That is one fancy way of thinking about a very simple idea. Okay. All right. So the next thing that is done usually in digital systems is some kind of a state diagram, right, and state diagram here will be quite simple. Okay, so there are only 2-bit states. Okay, so let us do a state diagram. There are only 4 possible states, 0 0. Okay, from 0 0 what states can you go to? Remember, I have a sequence of d flip flops and I am bringing in bits from the left. So how do I do a state diagram? I have to now think about what next state I can go to, but basically what input will come in. Okay, I am in state 0 0, what input will come in? It can either be 0 or 1. If a 0 comes in, what will be my next state? I will continue to be in 0 0. Okay, what will be my output? I am in state 0 0 and then 0 is coming in, my output will be both zeros. Okay, so this is a very standard way of denoting a state diagram. In case I am in 0 0 and an input 1 comes in, what state will I go to? 1 0. Okay, so of course the convention is important. I am going to write always S1 S2. Okay, the first D flip flop first. Okay, you can also do it ulta, then everything will change. Okay, so but I am going to write it as S1 S2. Okay, so the next state can also be 1 0 if the input is 1, in which case the output will be 1 1. Right, just a question of looking at that state machine and figuring out what is happening. It is a simple D flip flop, so it is not too hard. Okay. Now from 1 0 what can happen? Input can be 0, which means I will go to 0 1 with an output of 0 1. Okay. Or input could be 1, in which case I will go to 1 1 and the output will be 1 0. Okay, maybe my picture is going to look really ugly, but anyway it will be accurate. It is the only thing I can guarantee. Okay. Okay. So now from 0 1 what can happen? If my input is 0, 0 0. Okay, so I am going to make my picture a little bit more beautiful. Okay, so let us say we do this differently. Okay, so we will say if my input is 1, if my input is 0, I go to 0 1 with an output 0 1, right, and if my input is 1, I go to 1 1 with an output 1 0. Okay, so this will make the picture a little bit better. Okay, now from 0 1 if the input is 0, I am going to go to 0 0 with some output, and if the input is 1, I am going to go back to 1 0 with some output. Okay, and at 1 1 if the input is 1, I am going to stay here. If 1 1 the input is 0, I am going to stay, I am going to go here. Okay, you can fill out the corresponding things. I think this will be 0 0 and 0 1, so this will be 1 0 and this will be 1 1. Okay. Okay, so this is a state diagram that you can fill out. Okay, so I did it rather quickly, but I think this is quite basic, and you might be able to do it if you give it some thought. Okay, so what's the utility of the state diagram? What do you do with the state diagram? I learnt it long back in. Okay, actually time is missing in this picture. Okay, so it's a bit of a problem. So people we will change this diagram soon enough, but but the idea is basically, as the state evolves, you can see how the state is going to evolve from time to time. That's the idea in the state diagram, and in there are general system theoretic ways of saying which state diagrams are good, which state diagrams are bad, etc. These things are used in convolutional codes also, but we won't go into all that detail in this course. Okay, so we'll simply look at it and say it's one more thing that we can do with the convolutional code. Okay, so that's nice, but let me ask you some questions. Okay, where are you to begin with? 0 0. From 0 0 you can possibly go only to two other states, 1 0 and 0 1. Okay, 1 0 and 0 0, I'm sorry only two other states, that's correct, but not 0 1 0 1, but 1 0 and 0 0. So the path you take gets defined on the state. Okay, so any input sequence you have can be mapped into a path on the state diagram, right? Starting at the all 0, you will go to something and you can map that path. Okay, but along with the 0 termination, what else can I do? I can come back to the all 0 state. So in fact, from any other state you can come back to the all 0 state in 2 steps. You do that, and along that path both the input and the output are clearly represented. Okay, so the input, you know what it is, and the message is there, and the code word is also there. Okay, so paths on the state diagram are important. Correspond to message / code word. That is one thing. The other idea, which is also very important, that the state diagram conveys is, no matter how long my input bit sequence is, my input bit sequence can be 8 or can be 8000, okay, my state diagram still has only 4 states. Just because my number of input bits goes up, my state complexity is not going to increase, the number of states is not going to go up. Okay, that is a reassuring thing when you see the state diagram. Okay, so that is something that is exploited in the decoding. Okay, no matter how long the decoder is, the number of code word bits is, anyway it comes only from a 4 state system. So there is some structure which can be exploited in the decoding. Okay, but coming back to the point that was made about the time axis, the time is kind of explicitly not present in the state diagram. Okay, so it's implicit, you should know where you are, should have a count of how many hops you did from state to state to know time. Okay, so that problem is rectified when you go from state diagram to what's called a trellis diagram. Okay, so you move to a trellis diagram, and there you explicitly use a time axis and draw different state diagrams for different times. That's what you do. Okay, so you don't have the same state. For instance, this 0 0, right, you have this one state for any time. Okay, so it's just that you split it up and draw it for different times, and then the picture becomes a little bit cleaner, and you can think about your decoding and encoding very nicely in the trellis diagram. Okay, the trellis diagram is very standard, and that's what's used most of the time. Okay, so let's do the trellis. Is there a comment or some question? No. Okay, so what you do in the trellis diagram is, yeah, so you are going to draw. So let me draw an arbitrary stage. Okay, instead of starting from 0 0 etc., let me draw an arbitrary state somewhere in the middle. Okay, so you can be in any one of the 4 states, 0 0, 0 1, 1 0 or 1 1. Okay, and the next state, okay, is going to be again one of 4 possibilities, but instead of drawing them, instead of assuming that the same 0 0 state represents the state at the next instant, I will draw one more set of states. Okay, so this is the state before some time I. Okay, so this is time I. Okay, before the ith input is clocked in, these are the states. Okay, after the ith input is clocked in, these are the states. So, maybe I can call this state as S I and this will be S I plus 1, okay, right. So, if S I is 1 0, what does it mean? I was at state 1 0 after I minus 1 bits have been clocked in and before the ith bit is clocked in, okay. So, now I can do links here, okay. So, what will be now I can join these two things, okay, that was something fancy, I did not do it, did it on its own I think, okay, that's nice, okay. So, if 1 comes in it is going to go all the way down here, okay. Now, from 0 1 also same thing will happen, 1 0 and 1 1 same thing happens, and now I can write my input and output on this, okay, 0 0 0, oh my god. Is this correct? Let me know if I am making a mistake. Huh? Let me go back to the state diagram and make sure out of 0 1, out of 1 0 with the 0 you get 0 1. Okay. So, the same thing as the state diagram, okay. So, it is exactly the same, there is nothing that has changed except that now my branches go from one state to some other state, so to speak, at the next time, that is all. So, this is called a trellis diagram, the ith general stage of a trellis diagram, okay. So, this is called one stage of a trellis, okay. So, at each stage you get one input bit and two output bits. So, once again I am talking about this example, but if the example were if the encoder were something else, it is easy to see that you can reconstruct a very similar diagram, okay. So, you have a state diagram and then you can convert it definitely into a trellis diagram, there is no problem, okay. So, the ideas are quite clear, okay. So, now what do I do if I have k input bits, okay. So, I have to start at time 0, but at time 0 there is something slightly special going on, okay, because I know already that there is only state 0 0. Okay. So, at time 0 I can either get a 0 which means I will continue to be in state 0 0, or I can get a 1 which means I can go to state 1 0. So, what happens at time 1? At time 1 the trellis becomes, after time 1 the trellis becomes full, right, all the states can be occupied. Okay. After this you have the complete stage, right. So, this is the time axis, you have 0 1 so on, okay, you have to go all the way up to k minus 1. Okay. So, I am going to put dot 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 here, basically you can fill it out, and then after the, so let me draw the k minus 1 a little bit more later. This is S k minus 1, okay. So, this is after the k minus 1 thing has been clocked in, okay. So, this is how the trellis will look, okay, the entire trellis if you want to do it for the entire input, okay. So, you have k minus 1 inputs, at the end of the k minus 1 bit, or no, and it was the kth bit, which is you will be in S k minus 1, am I right, or is it S k? Okay. So, I think I should do S k here. So, let me do the, let me change this out, let this be S k. Okay. After the k minus 1, after the kth bit has been clocked in, you will be in Sk, okay. Is that right? When I say kth bit, you should remember it is numbered from 0 to k minus 1. So, let me say k minus 1th bit instead of saying. So, we will start at 0th bit, 0th bit, first bit, so on till k minus 1th bit. Okay. So, after the k minus 1th bit is clocked in, after u k minus 1 is clocked in, you will be in escape. Okay. What will happen next? I am going to be clocking in only 0. Okay. So, when you do 0, then the states you can have is only 0 0 and 0 1. Okay. You cannot have anything else. Okay. And then finally, one more 0 will take you to 0. Okay. So, this is time k and then k plus 1. Okay. So, we have the 0th stage, first stage, so on till a general ith stage, and then a k minus 1th stage, which is the last message bit coming in, and then you have the kth stage where you input a 0, k plus 1 stage where you again input a 0, take it back to the all 0 state. Okay. So, this is how an entire trellis diagram will look for the convolutional encoder that we had for the simple example. Okay. If you have some other example, it is easy to see that the similar diagram can be redone. Okay. If you have mu bits in the state, okay, memory mu, then how many states will I have? 2 power mu. Okay. And then how many stages will it take? How many zeros do I have to clock in here? Mu zeros. Okay. So, I will go out to k plus mu minus 1. Okay. You start at 0 and go all the way to k plus mu minus 1 in general, and it will take mu bits to be clocked in before reaching all the 2 power mu. Okay. So, we will not reach it immediately. Okay. You will have only 2 states after the 0th stage, you will have 4 after the first 8, so on till 2 power mu after the mu bits have been clocked in. So, that will be the general picture. There is no point in drawing the general picture because I think the intuition is clear in this. Okay. So, you see this is a directed trellis. Okay. So, we have direction, that is because we are going from left to right, that is the idea here. We are starting at the all 0 state and ending at the all 0 state. Okay. And the analogy that I had before for about paths is also true here. Okay. Every set of inputs that I have will correspond to a path on the trellis. Okay. If you have 2 different inputs, there will be 2 different paths, they will never be the same. Okay. So, that is the idea. Okay. So, let me fill it out and then okay. So, let me just do this. Okay. So, every message sequence you have, or every code word sequence you have, corresponds to a path in the trellis. Okay. So, path in a trellis, paths in trellis correspond to message and code word pair. Okay. All right. So, this in this diagram, how many different paths are there? 2 per k, right. So, there has to be exactly 2 per k paths. Okay. So, you do not have to worry about counting the paths once again. Why should I not have to worry about counting the paths once again? Every path corresponds to a unique message, right. So, how many possible messages are there? 2 per k. Okay. And there will be exactly 2 per k paths, no problem. Okay. So, there are 2 per k paths. Okay. There are various other ways of counting that also, but anyway you get 2 per k paths, there is no problem there. Okay. So, this intuition is crucial in the decoding. Okay. The fact that every code word, every message corresponds to a path. Remember, what do we have to do when we do ML decoding? We have to do correlations, right, or minimize the Euclidean distance. Okay. So, you have to do some kind of a distance for every of the received word with every possible code word and pick that code word which gave you the least distance. That is the idea in ML decoding. Okay. What people will do in this trellis diagram is, you do not compute the distance in one shot for all the code words or for all the code word positions. You start from the left and keep accumulating distance as you go along. You will see as you go along, you can eliminate a lot of paths very early. You do not have to wait. I mean, in every state you will see you can eliminate a lot of paths. In fact, it is enough if you retain only 4 paths in this. Okay. You do not have to keep doing that computation for all the 2 power k paths. Okay. Initially ML is scary because you have to do 2 power k correlations, 2 power k computation of distance. It turns out in the trellis it is enough if you do for 4, okay, roughly 4. So, 4, not exactly 4, you have to do some more calculations, but you have to do only, you have to only keep 4 in mind all the time. Okay. You do not have to worry about it because you can keep eliminating as you go along. You are starting at all 0, ending at all 0, and that is the key behind the decoder. Okay. So, we will pick up from here in the next class.